And hello. In today's video, we'll go over what an exponential function is, how to evaluate and sketch the graph, what the parent function looks like, and how to graph by transformations, as well as an application problem or two. So first, what is an exponential function? An exponential function is some function where our variable is in the exponent. We call the number that we've taken to the exponent the base. And again, our exponent has to have our variable. So we'll evaluate and sketch a couple of graphs. We just need to be careful to plug the variable in to the exponent and simplify. So 1.5 to the first power is 1.5. Squared means multiplied by itself, so that's 2.25. Anything taken to the 0th power is 1. A negative exponent is the same as the reciprocal, so 1.5 to the negative first power is 1 over 1.5, which you can reduce that fraction to 2/3. One over 2.25 is 4 over 9. So let's sketch our graph. What does this actually look like? Well, we had 0, 1. And then as we go down the line, each point is multiplied 1.5 times bigger. So something along these lines. And then as we go the other direction, each point is divided by 1.5. What that means is it'll never actually hit 0 that way, and it'll kind of race off quicker and quicker to the right. Similarly, on this next function, 30 times 0.8 to the x, we just need to be careful of our order of operations when we're plugging something in. 30 times 0.8 to the x, if I were to plug in a 1, that's 30 times 0.8 to the first power. And our order of operations tells us to evaluate the exponential part first. 0.8 to the first is 0.8, and then multiply by 30 is 24. If I want to plug in a 2, I would need to evaluate 0.8 squared first, which is 0.64, and then multiply that by 30, which is 19.2. Again, anything to the 0th power is 1, so this is 30 times 1. Again, order of operations, use your calculator to evaluate 0.8 to the negative first if need be. That's 1 over 0.8, and then multiply that 30 and you get 37.5. And then this next one will be the same as 1 over 0.64, right? That was 0.8 squared. And then we would multiply by 30 to get 46.875. So if we wanted to sketch, we have a graph that kind of looks like this, roughly. It's going down further and further to the right, and you can see as we multiply 30 by more and more part 8s, the number keeps getting smaller, but it's never going to cross 0. So now we can see we have our two flavors of exponential functions. If our base is greater than 1, we have what's called exponential growth. If our base is less than 1, we have what's called exponential decay. Because we have multiple varieties of exponential functions, there's no one singular parent function. So let's graph one growth function and one decay function, so we can get a handle on the basic properties of some of these exponential graphs. So here we have 2 to the x. So first, let's plug in 1. F of 1, 2 to the first power is 2. F of 0 is 1. Again, this is exponential growth. Our exponential decay will just work in the opposite direction. So a couple of things to note about these exponential functions. First, the domain is always all real numbers. Our domain is always negative infinity to infinity for an exponential function. Our range of the parent functions is 0 to infinity, but it does not actually include 0. There's no exponent I can put on 2 to make it 0. I can make it very close, but not exactly. Each graph had a y-intercept of 1. As long as there are no transformations, it will always have a y-intercept of 1 and no x-intercepts. It has no x-intercept because it has an asymptote at y equals 0. Now, as we add transformations, that'll shift where our x-intercept is or where our y-intercept is. As we add transformations, that'll change where our y-intercept is, where our asymptote is. So we'll explore those when we get to those. A couple of reference points. It's important to note that each time we plugged in 1, we got our base. And then when we plugged in -1, you get 1 over the base. So these 2 points will help us as we graph, and then our transformations will just adjust these figures. So here I have the function 3 to the x that I would like to graph. First, this is an exponential growth because our base is greater than 1. But that negative tells us that it's been flipped over the x-axis. So let's use what we know about exponential functions to graph 3 to the x, and then we'll reflect it over the x-axis. So 3 to the x should have a point at 0, 1, a point 1, 3, and -1, 1/3. So that's 3 to the x. -3 to the x is then reflected over the x-axis. So that's the graph of y equals -3 to the x. 1/2 to the x minus 2 plus 3 is an exponential decay function that has then been shifted right 2 and up 3. So first I'll start with our exponential decay function 1/2 to the x. Again, it should have the point 0, 1, 1, 1/2, and -1, 2. And then I can just add 2 to each x coordinate, add 3 to each y coordinate. Now, this does change the asymptote. Because we're shifting it up 3, our asymptote is actually at y equals 3. So the asymptote always follows our translation up or down. Compound interest with banks, things gaining or losing value over time, are all going to be exponential growth or exponential decay. Here we have a truck that loses 9.5% value each year, and I want to know, when is its value $5,000? If our truck loses 9.5% each year, that means it's only going to be worth 90.5% after each year. So after 1 year, it's going to be worth 30,000 multiplied by 0.905. After 2 years, we'd multiply another 0.905 in. After 3 years, we'd multiply another 0.905. So our variable is in the exponent. Here we have 30 times 0.905 to the x. So at the start, our truck is worth $30,000. So by plugging in 2, we can see it's just a little bit under $25,000. If I plug in 4, it's right around $20,000. So it shrunk a little bit less over the next 2 years. In another 2 years, after 6 years, it's worth about $16,000. After 8 years, it's worth about $13,500. Right? It should be slowing down as we go. After 10 years, we're still above 10,000 at 11,000 or so. After 12 years, we're at 9,000. After 14, we're at 7. 16, we're at 6. So it's probably going to happen somewhere in the near future. At 18 years, we are just a hair below $5,000. So we can solve this equation. We could solve this equation graphically by graphing our exponential function and then also graphing the line y equals 5,000. And finding where those 2 points intersect, which is right around 18 years.